couple of ways to approach problems like this. We've talked about them before, but just a quick review. If we go to positive or negative infinity, that means if we were looking at a graph, we would go, in this case, really, really far to the left, right? So all this extra stuff that's happening in the middle isn't going to affect where the limit's headed as the far, far left goes. So in that case, what we do is we only look at the leading coefficient in the highest degree, and all the extra little stuff like this minus 2x squared, that's going to go away, right? It's going to kind of not be affected by this going really, really far to the left. And same thing here. Now, you can kind of see I tried to trick you guys a little bit because we're looking at the largest exponent, which is a positive x to the 3x to the fifth. So this little 6x squared isn't going to do much. And what we have is we have our end behavior result. So, this a little bit better. So what we talked about last week was we can really just look at each of these pieces individually. The largest degree and coefficient up top over the largest degree on bottom. Well, if we do that, notice what happens. I've got an x to the third and x to the fifth. This x to the third is going to cross out with 3 of the x's on the bottom. So what's really left over is a new item or a new limit that looks like this. Now we get to the point where what happens is x goes to negative infinity. Well, what if I just plugged in negative infinity? If I just plugged in negative infinity here, negative infinity squared is going to give me a positive infinity. Positive infinity times 3 is still positive infinity. So now I have 4 divided by infinity. The way I like to think of this is, what if I have a rope that's 4 feet long, and I cut it into an infinite amount of pieces? How big is one of those pieces? It's so small that it's basically 0. So this is the way to do it without a graph. Now I don't really know what this graph looks like. I have no idea without graphing it, but I do know that something weird is gonna happen here. I don't know if it's actually not gonna be connected. There might be some asymptotes. But I know that as I go to the far, far, far left of my graph, I'm gonna approach either 0 from the top, or maybe it's gonna look like this from the bottom. But either way, it's going to approach 0. And the end behavior model right here really only focuses on this part of the graph because we don't care about what that middle part of the graph looks like. What's happening as I go to the far, far left or the far, far right. Right, so you can graph this and confirm. You should get the limit of 0. Now, same idea with this one. The only difference is this isn't a rational function. It's not a fraction. So there's nothing to reduce out, but what happens if I plug positive infinity in? Right? That's a really big number. Biggest thing we can think of, we're going to plug it in for x's. Well, what happens here is that the highest power, that x to the fifth, is going to control everything. It's going to be the most powerful thing. That's going to tell us how this function behaves. So we don't really care about all this extra little fluff. That's not going to matter when we think about it big, big picture. So the limit as x goes to infinity can really just be determined by this piece, negative 2 times x to the fifth. So what are we going to do? We're going to plug in negative 2 times infinity to the fifth power. We're going to plug infinity in. And then we're going to evaluate, well, infinity to the fifth power is still infinity. Timesing it by negative 2 isn't really going to change it other than the fact that it makes it negative infinity. So what do I know about this graph? Right? I don't really know what this graph looks like, other than it has an odd degree. So I know that one end is up and one end is down in terms of its graph. So if I was going to create a graph, I know that it's also negative. So it's going to start high and low. I don't care what's happening in the middle, but I know that it's going to go as x goes to positive infinity. Right? As my x's keep going to the far, far right, I can tell my function is going down. So I always had kids not have a very strong concept with dealing with values as x goes to positive or negative infinity. If you have a calculator, plugging this into your calculator can give you the graph and confirm what's going on. But this is just two ways to do it without a graph. So I was looking back at a couple of things. First off, I was looking back at homework. Yikes. If you were to look at my gradebook, you would see a whole lot of red. Red is missing assignments. And some of us have maybe one, some of us have none. But some of us have 10 to 15, 20 missing assignments. The gradebook is 100% up to date as of an hour ago. If you are missing anything, we are currently right here, and we're going to do limits algebraically. And then we've got next Thursday, we got a quiz, and then we've got to review our final. But the part I want to point out is that my gradebook officially closes for any late work, anything at all that you're going to turn in. You have until May 27th. And some of us, this quiz could dip us below passing. This test could definitely dip us below passing if we don't do our homework and get on top of it. So, hopefully you're going to look at your grade at some point in the next couple hours, and you're going to see what you're missing, and you're going to have a very strong push to get that stuff turned in. We will be taking our final, which I use the word final, but it's not. It's the same value as a regular test. So we're going to take our limit and review test on Thursday the 27th, which is the same day as the gradebook close. After that, you can't turn anything in. Friday, I will be grading Thursday night, and Friday you'll have your grade, and seniors, you're going to have your last chance to do remediation on that test. So I just want you guys to be well prepared and understand everything that's coming forth in the next couple of days. I think we mentioned this, but this last week of school is just a catch up. Like that would be basically for juniors. We're going to say, hey, here's a survey, fill it out, look at your grade. Do you have any questions? No, you're good? All right, have a great summer. So we really only have 2 weeks of actual stuff to get done and to be productive. Okay, so I was looking through some old homework, and I noticed that we were really struggling with how to do delta math and tables, and I will take blame for that. I made an assumption that was definitely not true. So we're going to just quickly confirm this. So sometimes you were asked to find a limit via a table, and we had different types. So let me show you this right here. This is just an example. I don't know if I can make this bigger. That should be better. So the directions say, enter x values into the table below to determine the function's value for f of x at various inputs. Use the function in order to determine the answer to each question. So we've got to find the left-handed limit, the right-handed limit, the two-handed limit, and the point, all using this table. Well, let's start with the point, because I think that's the easiest. Right? All you do is type in -5 and hit try value. Okay, -5 is undefined. So, I think I can just click on that, and it'll type undefined. But what about the left-handed limit as we approach -5? So, you can clear the table if you want. I need to pick values that are to the left of -5. So that's numbers past -5. So that's a number like -5.1. Right? Then I'll hit try value. Okay, now that doesn't tell me much. So what if I go negative 5.01? Try value. That tells me a little bit, but I need more. I need to get closer and closer and closer to negative 5. So notice I'm just making this number as close to negative 5 from the left-hand side as I can. And do you see the limit starting to form? The limit is the output. And what number am I getting close to? Well, we're getting close to negative 4 here. So I'll type negative 4 in. But now I have to try the limit to the right of negative 5. So I'm thinking, let's clear this. And I want numbers that are to the right of negative 5. If you're not positive on this, draw a number line. I don't think I can draw on this. Maybe I can. Oh, there I can. Start here at negative 5. What numbers are to the left? Well, those are numbers like negative 5.0, negative 5.00. What numbers are to the right? Those are numbers that are going to be like negative 4.9, negative 4.999. And our goal is what happens as we get closer to the actual value of negative 5 for both the left and the right. So, what we need to do then is I want to try negative 4.9 because that's to the right of negative 5. And then I want to get closer to negative 5. So I'm just going to put another 9 there. Negative 4.99. Try that. Try another one. Try another one. Oops. And you can see we're actually getting closer and closer to negative 4. So now we need to say, well, wait a minute. The left-handed limit has the same value as the right-handed limit. If the left and the right-handed limits are equal, that means that the two-handed limit itself is equal. Okay? And then I'll submit. And you can see we got that one there. So let me go back quick. You had other questions that were just like this, where let me get rid of all that. All right, so same type of question, but now they're going to say, well, what happens as x goes to negative infinity? Now notice, we don't know what the function is. So I want to pick values that go to negative infinity. Well, what's a really large negative number? We can try negative 10,000. Let's add another 0. Let's add another 0. Let's keep adding zeros. Let's go really crazy. And you notice these numbers are huge, right? They're really large negative numbers, and it's approaching negative 0.8. That's what the output is approaching. Okay. And then we got to go to positive infinity. So I'm going to clear that. This time I'm going to just start with a really large positive value. And I'm just going to keep adding a couple zeros here. Now notice, we're jumping all over the place. These outputs are not, oops, I accidentally hit the wrong one. These outputs aren't kind of getting constant or steady towards the same value. And what that means is we might have an oscillating function that goes up and down, up and down. Notice how we go from some negative to some positive. So I'm trying some really large numbers, and I'm not getting any concrete output. I'm not headed anywhere, which means this limit does not exist. All right, so there was one more I wanted to show you, and I'm going to do this. I'm going to cheat in a second just to see. Yeah, see, that one works. I want to show you one that doesn't work. That's not a bad one, actually. Let's look at this one quick. So same thing, but now we're approaching 5 from the left. So think of where 5 would be on the number line. Numbers that are to the left of 5 are something like 4.9, 4.99, 4.999, notice my numbers are not getting constant. They're not the same thing. It actually keeps growing. Right? This is getting bigger, bigger, and bigger. It's headed towards negative infinity. Right? So if I clear the table, what if I do numbers that are to the right of 5? So that would be numbers like 5.1, 5.01, 001. Keep adding zeros. See how it's growing and growing and growing? That means that our function is headed towards a very large output, which is positive infinity. If the left-handed limit does not equal the right-handed limit, then this function does not exist. Okay. Now what about f of 5? I'm just going to clear the table. What if I plug exactly 5 in here? It says it's undefined. All right, so I just noticed that that was an issue on a lot of people's homework. So hopefully that just gave you some feedback on how those tables can work. We did talk about how to do them in our calculator, but I think students were really confused with how the tables worked in Delta Math. All right, so we're going to shift our thinking here, and we're going to review some rules for limits. But our hint is, let's think about what we already know. We're going to make some generalizations here in general. So I'll give you a second to copy. We'll just start with this one and do it. Leave yourself a little bit of room here, because we want more than just the answer. We want to know why. Why is this true? And I will just let you in on a little hint. These limit rules, I know it doesn't make a lot of sense to you right now, but these limit rules are the same rules that will be applied to derivatives and integrals in calculus. So if you can be really comfortable with these rules from this year, we'll review them next year when you're in calculus, and then we're going to keep building on them. So just hopefully that's a little bit of buy-in of what we're doing today. All right, let's think of this graphically. If I have the limit of 5, well, let's think about how this is set up. What is 5? That's my function. It's telling me that f of x is equal to 5. Or y is equal to 5. So what if I drew a graph? That graph is just a vertical line, a horizontal line at the equation f of x is equal to 5. So now what is the limit as x approaches 3? So as I approach 3, what's my output? 5, right? Does it matter what x is? What if x was 10? I would just go further out here, but my line will always be 5. Now here's the important thing. If you're taking the limit of a constant, 5 is what we call a constant because it's consistently that output. The limit is always 5. So you don't need a graph. You just know that that's one of the rules. The limit of any constant is always itself. Now, what if we switch it and say the limit of x? Now, this equation right here, we know what the graph of x looks like. Y equals x. It's a slope of 1. We're going to do a very rough sketch here. We're going to graph the equation f of x is equal to x. So if we think graphically about these limits, it makes them much, much friendlier. So what would happen if I approach 3? Well, and I should have made this comment on the first one as well. When I'm talking about limits, these are two-handed limits. It's not a left-handed side, it's not a right-handed side, it's both of them. So, as we can see here, the limit from the left-hand side and the limit from the right-hand side are going to touch. Right? They're going to approach the same value. So what is that limit? If 3 goes into the function, what's going to come out? This is the equation is whatever x is, that's what y is. So you can kind of just check from our knowledge on that graph that that's what the limit is. And that's one of the hints, is these rules that we're teaching you can all be visualized graphically. Now eventually you're going to start seeing where I'm headed with this. But let's look at this graph. Okay, the function itself is a linear equation, 3x minus 4. Now let's draw a fairly accurate graph here. If I have 3x minus 4, 1, 2, 3, 4, we know we have a y-intercept of negative 4, and my slope is 3. So go up 3 over 1, up 3 over 1, and we're going to do that until we pass x equals 2. We'll start at negative 4. Rise is 3, 1, 2, 3, run is 1. Rise is 3, 1, 2, 3, run is 1. And rise is 3, run is 1. If we had graph paper, it would look like a much better graph. But there's my equation. Y equals 3x minus 4. I need to figure out what is the limit as x approaches 2. So, if we're thinking about this graphically, the limit from the left has to approach the limit from the right. Now, where is it going to hit? At the y value x equals 2. So, the limit as x approaches 3x minus 4, or excuse me, the limit of 3x minus 4 as x approaches 2 is equal to 2. Now, does anybody see a faster way of doing this instead of just drawing a graph? So what's going to happen is the functions are going to get more challenging. Well, we're not going to always know exactly what they look like. So I won't give you the hint yet, but there's a little bit of a shortcut. So let's think about 4x to the third. Now we're going to make a graph for this one as well. And I want to go out for sure to x equals 3. But I think this graph is going to be pretty large. Well, let's think about this just in terms of what if I graph 4x to the third and I start with 0. If I have 0 in here, 0 to the third power times 4 is 0. If I have 1 in here, 1 to the third power times 4 is 4. So I'd be up here at 4. But then when I do 2, 2 to the third power is 8. 8 times 4 is 32. So I'd be way up here. And you might know something about this graph already. This is the graph of a cubic function. So instead of trying to figure out graphically what this is, what we're really doing is we're saying, you know what? Every graph we looked at so far is continuous. There isn't a break in the graph. There's not piecewise. There's not two different parts. It's one continuous function. And anytime you have a polynomial, which all of these are some form of a polynomial, it's always going to be a continuous function, which means to evaluate this limit, all we have to do is plug in direct substitution. Because we know that wherever this output ends up being, the left-handed side and the right-handed side are going to meet because of this idea of a continuous function. So, 3 to the third power is 27. 27 times 4 is that 108. Okay. I want to double check my math there. That's good. Okay. So, here's the idea. If you just have a polynomial function This is called direct substitution. You just plug in the value. You don't need a graph, but hopefully this graph all makes sense. That's how we built it on limits. We looked at it graphically first, and now we're getting to the algebraic side. So, if you want to title this up top, I didn't call it this yet, but all we did was direct substitution. And that's where you take that x value and you just plug it in for x. You have to be careful because that's not always going to work. So what about these? And we're actually going to not do the think graphically. You might know a little bit about these graphs. I'm going to just draw a very rough sketch. So you don't have to draw this sketch because it's not going to be accurate. But if I have the square root, square function graph looks like this. Because any positive number, including 0, can be plugged in. However, the extra 4x plus 1 is going to change my graph a little bit. And if I don't have a calculator handy, the only thing that I know is that as x goes to 6, somewhere around here, the left-handed and right-handed sides, that's still a continuous function for every value that works. So all that means is, you know what? I can just do direct substitution here. And that's what we're going to do. We're just going to plug in 6. Because we're confident in the fact that this is a continuous function, I know that just plugging 6 in and simplifying will give me my answer. The output, when x is 6, the output is going to hit 5. If this was an accurate sketch of my graph, oops, it's not. Definitely not. But if you were to graph it, you would see that the left-handed and the right-handed limits both approach the same value of 5. So, I want you to try this one. You don't have to create a graph. Go ahead and try direct substitution and see what you get. And remember, that's an exponent there. So what do we do? Take the fact that x approaches 1, and you can do as much as you want in your head, or you control all your steps. 1 squared is 1, 1 plus 2 is 3, 5 to the 5th power is 125. So, that's pretty friendly, right? I could have just told you that at the start. Hey, just plug that number in and evaluate. But it only works when we have continuous functions. Now, if you were to graph this function, 5 to the x squared plus 2, its graph is going to look kind of exponentially, but that's still continuous. So we don't run into any problems with direct substitution when we have continuous functions. I'd like you to try this. Determine the limit of the function as x goes to 0. Okay. So let's take a look here and see. My guess is you saw the 0 and you tried this. Which, if we simplify, is 0 over 0. Right? Now, if you have a calculator, grab it. Do 0 divided by 0. What does it say? Now, we're going to throw out a calculus term here in general, but this is called the indeterminate form, which the big thing is we can't divide by 0. Right? That's one of the 10 commandments of math. Thou shalt not divide by 0. It doesn't matter what's on top. But what happens then? What happens when direct substitution produces an undefined result or an undefined solution? And this is the big part of what we're getting to today. So when you try direct substitution and it doesn't work, this is not an answer we want to see. It's not saying that there isn't an answer, but is there anything else we can do? Our good old friend algebra is going to come in and save us. Because what we're going to look at then is, you know what? This original limit can be changed. We can rewrite the meaning of the numerator and the denominator based off of one thing that we do. And most of the time, it's factoring. So what we're going to do is we're going to factor the top and factor the bottom. And just because I want to make sure you guys make this connection, I'm going to rewrite the original problem here. But what we're going to do is we're going to change the appearance. We're not changing the value or the meaning. But we're going to go ahead and factor this top part. If I have x squared minus x, what do those two pieces have in common? An x. So I'm going to factor one of the x's out, which leaves me with x minus 1. So again, nothing changed, we just changed the appearance. Okay. Lauren! Oh. Alright, and then we're going to do the same thing on the bottom. Now, they each also have an x in common. We're going to factor out an x from the bottom. What do you notice? By rewriting the new numerator and denominator, do you notice anything interesting? We're going to reduce out a common factor. This common factor of x times x is what caused the 0 over 0. We want to get rid of that by saying, you know what? If we get rid of that, it's a brand new limit, which now, let's plug 0 in for what's left over. 0 minus 1, 0 plus 6 gives me negative 1, 6. If you were to graph that, what would actually happen is there would be a hole at x equals 0. There would be an undefined point because the original function has this extra factor of x in it. So it would look like a hole. However, the limit from the left and the limit from the right are still exactly equal at negative 1, 6. So that's the goal today, is we're going to, if you get 0 over 0, we're going to try to apply algebra. So now, I mean, technically that's it, but we're going to look at a couple more problems that are just more unique so you can get used to the factoring side. So I'll do these two with you, and then the next two we're going to have you do on your own. Actually, I don't even think you need to do the first one. It's almost identical. There's nothing super crazy, so don't write this first one. I don't think it's worth the time. The second one I will have you write. Notice, if everything has an x in it, and I plug in 0, if you can do this part in your head right here that I'm showing you, you don't need to write it. But notice, I get 0 over 0, indeterminate form, that does not make me happy. So all we're going to do is factor the top. Each one of those has an x in common. And then we'll factor the bottom. And each one of those has an x in common. And that x over x reduces out. It reduces out because it's going to turn into the option of 1. And then I'm just going to plug 0 in here and here. So I'll get 2 over negative 5. That. Yeah. Alright, so that was almost identical to the one we did before. But let's write this one here. And I'm going to pull it down here just so we have more room to work. Now again, we should always check, because 7 isn't 0, right? This is the limit of x goes to 7. Well, I can plug 7 in, and I know that that might give me a nice answer. So we're going to check direct substitution right away. What happens if I just plug 7 in? 7 here, 7 here, 7 here. Now you might already know, but I get 7 squared is 49, minus 7 times 7, which is 49. I get 0. On the bottom, I get 7 squared minus 49, I get 0. There's my indeterminate form. Shoot. Direct substitution doesn't work. So what we need to do then is factor the top and factor the bottom. And really, the only way that these problems change is the factoring might get more challenging or just be a little different. Like up here, x squared minus 7x, well, that only has 2 terms, and each term has an x in common. I'm going to factor out an x from the top. Ooh, but what about this bottom? This is x squared minus 49. They don't have anything in common. But remember the box with the circle in it? That's saying that that middle term is 0. So what are the factors of negative 49 that add up to be 0? I know the x squared had to come from an x times an x. Where did the negative 49 come from? Negative 7 and a positive 7. Right? I just realized this doesn't look like 7. Well, now we're looking at reducing out a common factor. And this time it's not just an x in common. We have more than that. We've got a whole x minus 7 and an x minus 7 on top and on bottom. And what's left over now is just the x over the x plus 7. And now I can plug in 7. So we're going to do 7 over 7 plus 7. Which is 7/14, but we reduce that down to 1/2. Okay. So algebra, remember that algebra is your best friend when it comes to limits. If direct substitution doesn't work, try algebra. Now I will mention, algebra doesn't always work either, but that's something for another day. Okay, I'd like you to try these two. Factoring might get a little more challenging, but just remember your skills in factoring. So, kind of as I mentioned, you can confirm in your head if you just plug 6 into each spot. This is the way I do it. I'll get 6 squared, which is 36. 6 times negative 3 is negative 18. Negative 18 over negative 18, well, that for sure confirms that that top is going to go to 0. Right? And on the bottom, by plugging 6 here, I get 36 minus 36. We get 0 over 0. Indeterminate form, we don't like that. So my next move is to factor the top, and this is just do the box with the circle. Right? The factors of negative 18 that add up to give me the middle term, negative 3, are x minus 6 and x plus 3. And then if I factor the bottom, this is one of those special patterns that we get factors of negative 36 that add up to 0 are negative 6 and positive 6. So I kind of just saved a bunch of steps in one, but notice I got x minus 6 on top and on bottom. So this limit can really be written as just x plus 3 over x plus 6. We just reduce out that common factor, and now direct substitution will work, because 6 plus 3 over 6 plus 6 is 9/12, which divide by 3, we get 3/4. Same idea with the bottom one here. I'll scoot this up in a second so people maybe have a chance to write the first one. But I'm just going to check negative 2. Now you do have to be very careful with the fact that you're plugging a negative in and squaring it. So negative 2 squared is 4. So I get 4 minus 4 on the top. And then I get 4 plus negative 4 on the bottom. Which again, there's my indeterminate form. Doesn't work. So now we got to factor. So if I factor the top, x plus 2x minus 2. If I factor the bottom, this is the one where all I can do is pull out a common x on the bottom. But then we notice we have at least one common factor of x plus 2 on top and on bottom. So that allows me to just think of this limit. The answer to the limit is going to appear if I just think of it as x minus 2 over x. Now direct substitution could work. Again, it's not always guaranteed. But now I'm going to plug in negative 2 for each x. We get negative 4 over negative 2, which is 2. I really like this specific section because it takes this new idea of limits, applies the old knowledge of factoring, and then just blends it all together. It gives you a small taste of what calculus is like. Calculus says, hey, remember everything you've ever been taught from Algebra 1 all the way through pre-calc? Now let's apply it to new pieces. Alright, so big thing. Remember, gradebook closes on May 27th. You want to get all your missing work in by then. Homework tonight is Delta Math, 12.2 Day 1, Limits Algebraically. Try substitution first. If substitution doesn't work, then we'll go ahead and use algebra. Reduce it down, reduce common factors out. Alright, that's all I got. Have a great day. Adios.